Hello and welcome along. Now, it turns out there are two main types of telescope, reflecting telescopes and refracting telescopes. We're going to have a look through the pros and cons. So we'll start with refracting telescopes. Those are the ones that we've kind of discussed so far. They use a lens to bend the light, but a lens can't be made particularly big. There's a limit of around 1 meter. If you tried to make a 2 meter lens, it would bend under its own weight and that would degrade the image. And if you tried to make the lens thicker to make it stiffer and stronger, then it would just weigh more and that wouldn't really help. And you can't really put any kind of structure in place to hold it because that would block the light. And they also suffer from something called chromatic aberration, which you won't have heard of. We're going to investigate that now. So hopefully you'll have seen this image before, be aware of this and phenomenon called dispersion, where not all the wavelengths of light are bent by the same amount. And you can see very clearly in this picture, I found loads on the internet that were wrong, but this one is right, showing that red light, the longest wavelength light, is bent less than the blue light, which is refracted more. In terms of the physics of this, it's quite hard to explain, but I think the way I remember it in physics terms is that blue light is a higher frequency because it's a shorter wavelength, and because it vibrates faster in the glass, more vibrations per second, it's affected more by the glass than the red light. The other way of remembering this is red ahead. Red light is bent less. So let's have a look at how this affects the image from the lens. So what you can see here is that the blue light has been focused closer to the lens and the red light has been focused further away from the lens. Now, if you were looking at a star, because our vision is dominated by yellows and greens, which are the middle wavelengths, we would see a clear star image in the center, focused between the 2 points, focused between where the red rays and the blue rays cross. However, because that image would be surrounded by unfocused blue light and unfocused red light, it would look like there was a purple or magenta halo around the star, sometimes referred to as false color. And this is the first of 3 ray diagrams that you need to be able to draw. So in reality, all the big professional telescopes in the world are reflecting telescopes. And here's a picture of one, which just gives you an idea just how big they are. The biggest reflecting telescope in the world, that's a light reflecting telescope, is the Keck telescope. And here's a kind of mock-up of the mirror. It's made from individual panels that assemble to make that large mirror, and that's about 10 meters in diameter. And the reason they're made that big is almost completely just to collect as many photons as possible, to collect as much light as possible so they can see faint and dim objects. There are 2 main reasons why almost all the world of reflecting telescopes, professional astronomy uses reflecting telescopes. One is that we only need to accurately shape that top surface, and it needs to be accurately shaped, so much less than the wavelength of light. I think a really good mirror would be shaped within a 20th of the wavelength of light. But also we can put a really big, strong structure around the back of the mirror to support it, because that's never going to get in the way. To be honest, I'm not sure that structure behind isn't the one just for transporting, but it gives the idea there. We course one of the problems with having a reflecting telescope is it's sending the light back out in the wrong direction. So how do we ever get to see an image or take a photograph? And the most common arrangement is to have a secondary mirror. You can kind of see that towards the top right hand corner, and that reflects the light back through a hole in the center of the primary mirror, where it can then be seen by a camera or by the eye. So here's another ray diagram you need to be able to draw. This is what's called the Cassegrain arrangement. It consists of a concave primary mirror and a convex secondary mirror. I'll give you a few tips for drawing this. So start by drawing in the mirrors. Don't draw them too curved, and do make sure there's a hole in the middle of your primary mirror. Definitely put a point behind your secondary mirror like I have, so that your reflected rays from the primary mirror can be heading towards that, and then you can just add a little dotted line like I have, and then line up your solid ray on that line, and then it bounces back and they cross just behind the the primary mirror, and that's where the eyepiece would go. We don't need to be able to draw an eyepiece into this ray diagram. Other disadvantages, of course, that secondary mirror is clearly blocking off some of the light. Any light that hits the back of the secondary mirror isn't getting to the main mirror, and we're not going to see. And we also get diffraction around that secondary mirror, and that causes some degradation of the image. As I understand it, it's primarily a loss of contrast. You can see there are big spikes around the stars in this image, and actually that's caused by the metal supports, the rigid supports coming out and holding the secondary mirror, and they're causing diffraction as well, and that's what's causing those visible spikes. Yeah, so telescope mirrors can suffer from this phenomenon known as spherical aberration if we don't get the mirror the right shape, if we just grind it so it's kind of what's called a section of a sphere. And what would happen is that the rays that hit the edge of the mirror are brought to focus. They cross a little bit too close to the mirror compared to the rays which hit the middle of the mirror. And I'll show you that in a diagram. So you can see there the outer rays are brought together closer to the mirror than the inner rays. And that's a ray diagram you need to be able to draw. My tips are make sure you draw a nice smooth symmetrical curve to represent your mirror. Do draw where you want your rays to cross before you draw any rays. Make sure your incoming rays are nice and parallel. And make sure your rays actually do reflect on the surface of the mirror, not a bit behind or a bit in front, because I have seen examiners take marks off for that. So in summary, refracting telescopes, they don't have a secondary mirror to block light and cause extra diffraction. And this is highly prized in some fields of astronomy. Some amateur astronomers will pay thousands and thousands for a refracting telescope because it will take beautiful pictures of the night sky. You get a really good clear image, even though you can't necessarily see the most distant or the faintest of objects. And that's because there's none of this secondary mirror diffraction. Disadvantage is they can't be made very large because of the bending under the weight. They can suffer from chromatic aberration, and they have at least two surfaces to shape. So in reality, if you buy a refracting telescope, you would have either 2 or 3 lenses to reduce the chromatic aberration. So that then means 4 or 6 surfaces to shape. Now for a quick summary of reflecting telescopes, they can be made very large because we can put a structure behind to support the mirror. They don't suffer from chromatic aberration, and you only have one surface to be accurately shaped. The disadvantages, the cons, some light is blocked by the secondary mirror. The diffraction by the secondary mirror degrades the image. They can suffer from spherical aberration, and that can be solved or reduced by using a parabolic mirror. So in reality, all those professional telescopes have a parabolic mirror, so they don't suffer from spherical aberration. And although you need to know this balance of pros and cons, you also need to know the reality is that almost all professional telescopes are reflectors. Thank you very much.